All right, welcome. Let's go ahead and get started. Just a couple of reminders. I'm sure you're already aware we've got a homework assignment out. It is due, I believe, 1 week from today. So homework 1 is due 1 week from today. I think that's really all that's that should be on your agenda for the next week as far as this class goes. 1 week from today, as you turn in homework assignment 1, we are gonna get ready to work on homework assignment 2. And actually, it's wonderful that you're all here today because homework assignment 2 is directly related to what we're talking about today. So basically, I'm gonna ask you to implement the operations that we're going to talk about in class today. So the idea for this week is to introduce you to these operations and then get some practice using these operations, understand how we use these relational operations to execute queries, and then you'll go off and implement these as part of assignment 2. Are there any questions about assignment 1 or other things coming up on the schedule before we dive in and start talking? Yeah.
Just to clarify earlier, so the tests we have are all tests we graded on.
Yep, that's right. Any other questions? Yes.
The test updated because I couldn't see the update because of the code.
I did push an update to the tests. At least I thought I did a little while ago. I'm not going to check it right now, but I can check it after class and make sure that it actually happened. It's possible that I forgot to push or something. Yeah. But I thought that I had pushed a very small update to the test, so I'll double check that and post an announcement about it after class. Any other questions? All right, cool. So let's hop in and talk about relational operations. Before we do that, actually, before we talk about the operations themselves, quick little refresher over how we retrieve information using SQL, right? So quick rundown. These are the clauses that I introduced a while ago at the beginning of the course. And these are the ones that we're primarily focused on this semester. We'll see some other ones pop up. In fact, we're going to see some additional SQL enter our vocabulary today, a little bit later on, in fact. But these are the ones that I'm primarily interested in. And what we're going to talk about today is how we actually implement these clauses in our database management system. So real quick, what does select do with a query? What's that for? The columns, what columns I want. All right, what's the from clause do? Tables, okay. And then the where clause? It's a filter, it's a conditional, a filter operation. Order by is like the easiest one up there, I think. Sorting. And then group by is actually one of the more confusing ones. Does anybody remember what a group by is for? Good. Has to be used with an aggregate. So if I use an aggregate by itself, it aggregates the entire set, or actually a more proper term for that would be not a set, but what did we talk about last week? A relation. Yeah, aggregates over the entire relation. That's right. If I don't want to aggregate over the entire relation, but I want to aggregate over subsets of that relation, right? I would use the group by to specify what subsets I want to apply that aggregation to. Good, good. So what we're going to do next is talk about how this is actually implemented on our database using a concept called relational algebra. So anytime I give you a select statement, a query, we can break down that statement using relational algebra, which is really just a series of operations that are being performed on sets, or again, more formally, being performed on a relation. So these operations fall into two primary categories. Some of these I'm sure you will recognize from your set theory studies in prior courses. Some of these you probably have not seen or thought about before. They come in two flavors. So the unary types, right, have one operand, so that includes select, project, and rename. We'll talk about all these in a lot more detail in just a little bit. And then the relational types have two operands, and these are the ones that I'm betting you're probably more familiar with. Union, intersection, difference, and Cartesian product. And so what I want to do is kind of go down this list and talk about what each operation is for and how that applies to us in this class in terms of retrieving information from our database. So let's start at the top. We're going to start with the select operation, and this is very poorly named operation, I think, because it is not referring to the select clause of a SQL statement. So they happen to have the same name. I can understand why you would want to think that they are related, but they are not. They are not related. The select relational algebra operation specifies what tuples from a relation we want to keep based on some condition. So the way that we might see this written out in an algebraic form, I see the Greek letter, that's a lowercase sigma, I believe. And then I see some condition, higher date after January 1st, 1990, or higher date greater than January 1st, 1990, right? And then inside of the parentheses, I see the relation that I want this operation to be performed on. That is the syntax of using a select operation. So if I had to pair up this relational algebra operation to a SQL statement, what clause would it actually be paired up with? It's not select, but where? Yeah, it's where. So in this case, the select relational algebra operation is being matched up with the where clause of our SQL statement. Any questions on the syntax there? All right. Let's talk about some properties of this statement then, this operation. The result set, or the result relation, is going to have the same attributes as the relation that went in, meaning that if it's not affecting the number of columns, right? However many columns go in, that's exactly how many columns are going to come out. No effect on the columns whatsoever. It's also commutative. It's a commutative operation. So if I have two conditions, it doesn't matter what order I apply them in, right? As long as I apply both of those conditions, I should get the same result relation back out. That's actually going to be a very useful property to us in a week or two when we talk about optimization of queries. But for now, just keep that in the back of your mind. It is a commutative property. And for all these operations, we're also interested in the bound on the number of tuples. So if a relation has n tuples and I perform a selection on it, what's the upper bound on tuples that I would expect the result to have? Also n, right? It'd be a condition that doesn't match anything, which can happen. I mean, I don't necessarily know, right, if I'm going to find any matches or not when I write that where clause in my SQL statement. But the idea here is that it can affect the number of tuples coming out, but it doesn't necessarily have to change the number of tuples coming out. Yeah.
Is it a clause? You just said a clause that doesn't match anything. Would it be a clause that doesn't match anything, or a clause that matches everything?
Oh, I'm sorry. I got that backwards. Okay. A clause that matches everything. Yeah, a condition that matches every tuple. Sorry. The opposite could also happen, though. A clause that doesn't match anything could also happen. So absolutely will not touch what columns are present, but might affect the number of tuples that are present in the resulting relation. I'm also going to try and be very careful about the terms that I'm using here. You see the word set used here, but actually in many places in these slides and in general, I could replace that with the word relation, and it doesn't affect the meaning, right? Since relations are sets by definition. In fact, when talking about all of these operations, it's important to understand that the inputs are relations and the outputs are also relations. It's a very important piece to understand about the algebra, because I'm going to be using these operations chained together, right, in order to perform a query. So the output relation of one operation is going to be fed as the input relation to the next operation, so on and so forth, until I get my result. We'll take a look at that towards the end once we finish taking our tour of the different relational operations. All right, next up on our list is the project statement. So the project statement keeps certain columns and throws the rest out. And the syntax for a project statement is a Greek letter pi, followed by the names of the columns that I want to keep. So you see that list of columns, those are column names that I want to keep. If I have a column in my input relation, in this case employee is my input relation, if I have a column in my input relation that is not on that list, it gets chopped off and thrown in the garbage. What clause is this getting paired up with? Select. So this is the one that matches up with the select clause of a SQL query. All right. Let's talk about some properties of the project statement. Here's one important one. Duplicate tuples are going to get removed. How would this happen? How would I have duplicate tuples in my result? What would I need to do to get duplicate tuples in my result? I'm doing a projection here, right? So assuming that my starting relation has no duplicates, how could I perform a projection that then would have duplicates in it? What would I have to do? Yeah. If I don't include the primary key in my list of columns that I keep, then I run the risk. It's not a guarantee, but I'm running the risk of having duplicates in my results relation. And then it's going to remove those duplicates. Why? Because it's a relation, because it's a set, right? Because it's a set. Now, this is the theoretical definition of the project operation. Once you get to the implementation, once you start seeing this operation on the lab, you'll actually find that in practice, we usually don't do that. We keep the duplicates. We want to keep the duplicates. It's going to affect any computations, especially aggregates, if I remove duplicates in a lot of cases. So oftentimes we'll want to keep those duplicates. And so we sort of deviate from the theory a little bit here. Almost every SQL-oriented database does that, though. It kind of ignores that aspect of the projection operation, keeps the duplicate tuples, even though the official definition of relation says we should remove them. Does anybody know what it's called if we have a set with duplicate tuples? Anybody run into that before? A set with duplicate anything? What's that called? Anybody know? It's called a bag. So just keep that in mind. If you see that term, I know it's used in various textbooks and other papers and things you might read on the topic. So if you see a reference to a bag, that is a set that allows duplicates. Short and sweet definition. All right. Bound on the number of tuples. So if I feed in a relation with n tuples, I do a projection on a relation with n tuples. How many tuples do I expect to get back out? At most n. In fact, most of the time I expect the answer to be n, right? The only time I would have less than n would be if I remove some duplicates. That would be the only time that I would have fewer than n tuples. Is this commutative? If I have two projection statements, does it matter what order I execute them in? Can I execute them in whatever order I want and get the same result back out? What do we think? So remember, a projection is telling us what columns we want to keep, right? Columns we want to keep. So if I execute a projection, maybe one projection has column X and the other projection wants to keep column Y. If I execute the first projection and I keep column X, it's going to chop off everything, including column Y. Column Y is going to be chopped off as a result of that first projection. And so then when I run the second projection that says keep column Y and throw away everything else, what am I left with? Column Y is gone. I'm going to throw out everything that's not column Y, so I'm left with nothing. I'm left with the empty set. Right? Left with the empty set. If I switch the order, I actually get the empty set again. So that might trick you into thinking that it's commutative, but it's actually not. It's actually not. To consider why it's not commutative, consider if I have a projection that does X and Y, followed by a projection on just one of the two. Now I could potentially, I believe, have... Well, actually, no, this still doesn't really prove it, does it? Hang on. Let me think through this in my head real quick. That would keep X and Y. That would get rid of Y and leave me with X. This would keep just X. This would... Yeah, actually, that doesn't prove that it's not commutative either. What would be an example that proves that it's not commutative? Project. Well, I'm fairly certain that it's not commutative, but now I'm starting to doubt myself. Somebody help me out here. Does anybody think of an example? Yeah. Commutative means it doesn't matter if I have two operations of the same type. It doesn't matter what order I perform them in. It's gonna give me the same result back out. So classic example is addition, right? 7 plus 2 is the same as 2 plus 7. Sorry. Switch the order, it doesn't matter. I still get 9. So addition is therefore commutative. Subtraction is not commutative. The order that those numbers appear matters. Yes.
Well, I guess that my question is, aren't you essentially taking the intersection of all, whenever you do like sequential projections, aren't you just taking the intersection of their?
The result would be the intersection of whichever columns I'm requesting, I believe. Is that what you're trying to get at? So here the intersection is x, right? I get the intersection of those columns. Am I understanding that correctly?
Yeah.
So no matter what order I run these in, y is just not going to show up, right? Because it's going to get chopped off by this one eventually. That doesn't actually address whether it's commutative or not. I'm fairly certain that it's not commutative, but I'm struggling to come up with an example to prove it. I don't know. I might have to put a pin in that one and get back to you on that. Sorry that I don't have an example offhand to discuss that. I know it's referenced in the textbook, so I'll double check that one and get back to you either on Piazza or in class on Wednesday. Yeah.
Is it about the removal of duplicates?
Removal of duplicates. Oh, that's interesting. I hadn't thought about it from that perspective.
Like if you first x, y, z, and z is the primary key.
Yeah, you might be onto something there. Yeah, I think you might be onto something there, because if I project off the primary key, that's going to eliminate duplicates early, and then but no matter what, I'm going to project off the primary key. I'll have to think about it. You might be onto something. I don't want to spend all of class trying to figure this out, though, so I'm gonna go do some additional research and get back to you on this one. Any other questions about projection before we take a look at the next round, the next operation? So the next operation on our list is actually one that we have not talked about before now, but it's also a very simple one, a very straightforward one. It's a rename operation. So rename is represented by the Greek letter, I believe that's pho, right? Or rho, sorry. Pho is something else. That's rho. Anyway, it allows us to temporarily rename the column of a relation, an attribute of a relation, to some different name. Does anybody know what this would be in SQL? We haven't actually talked about it yet. Anybody with SQL background know what this would be? How to do that? It's as, yeah, the as keyword. So if I was doing this in SQL, where'd my chalk go? I had a good piece of chalk and now it's gone. There's a lot of bad pieces of chalk. If I had a SQL query, I could say select name as n. This is a rename operation. It's not permanent. This only renames this column for the duration of this query, right? It's not a permanent renaming. I can permanently rename columns. That's a different process. But this operation is talking about permanently temporarily renaming this column. Why? Why might this be something that we care about? Why might this be something that we want to do? Yeah. So for the sake of clarity in our queries, certainly is one reason why. There's a functional reason why as well, but that is a good reason. I'm always in favor of having clean queries, clean code. There's a functional reason why I might want to do that as well. I could have this column name show up in multiple different tables, right? That's possible. So the rename could serve a function of changing the name of one of them for the sake of this query so that I don't have that ambiguity in my query. I don't have that ambiguous situation to resolve as one possible case where that might be a requirement. And at any rate, as far as the relational operation goes, you can kind of see the way that it works is I use the Greek letter rho followed by what I want the names of the attributes to be in order as they appear in the relation that it's being provided. So this example is, we can infer from this example that this relation has 5 columns in it, and I want to rename those columns A1, A2, A3, A4, A5. Any questions? Yes?
Yeah, so is there a case where this is necessary? Because even though you have 2 columns with the same name, if they both are joined, then you can say student.id and then course.id. You don't have to.
So that's true as far as the implementation goes, but I think it's important to consider that we're talking about this from an algebraic perspective, paper and pencil theoretical perspective. While I think people would understand what you would say if you said course.id, and you might even see me write course.id, from a theoretical perspective, this operation is still strictly necessary because it's trying to define a consistent approach, a consistent algebraic approach to solving these queries, where implementations might take other shortcuts to do that same approach. And it's convenient to do it that way too, right? It's convenient to do it that way. Great question. Any other questions? Yes?
If you're not trying to rename all the columns, how would you specify?
Yeah, so if you're not trying to rename all the columns, I might say, old column equals new, or something like that, like a variable assignment type. Something along those lines. Good question. Any other questions? So those are all the unary operations, the ones that operate on single relations. So now we're on to the relational operations, the ones that operate on 2 relations. And these are the ones that are probably familiar to you from set theory. First one being a classic set theory operation of union. So if I'm unioning 2 relations together, that means it's going to include all of the tuples in both relations. All of them. And we can actually do this in SQL. This is something that is doable in SQL. You probably won't see it too terribly often. It does have some restrictions that we need to be careful about. I have to have the same number of columns, and the data types of those columns must match. So if I have, you can think of a union as actually a vertical, taking 2 relations and sticking them together vertically. That is my visualization of a union. And so the column data types have to line up. I have to have the same number, and the data types have to match in order for this to work. And the syntax for doing it in most implementations of SQL is, as you can see here, I actually write 2 select queries, and I just stick the word union in between. I wouldn't say this is a rare operation by any means, but certainly uncommon. You don't see it all the time. We actually have other operations that I expect to see more often that combine 2 relations together. But this is a relational operation, so included here for completeness sake. And then you can see the other relational operations from your set theory studies coming back. Intersection and difference. So just a quick review. Intersection being all tuples that are in both relations. So we were actually just talking about the intersection a second ago. If I have a tuple that shows up in both sets, then I'm going to include that in my result. If I have a tuple that only shows up in one side or the other, then I'm not going to include it. And then set difference is like subtraction. You should see it's even represented by the subtraction operator. Includes all tuples that are in R but not in S. This is very rarely used in practice. Intersection can be done. I have very, very rarely seen an intersection executed on a SQL statement, but the syntax for it is there. It does exist. Set difference really does not. exist in any meaningful way in any SQL language that I have seen. I've not seen an easy way to do set difference. Are these commutative? Is set intersection commutative? Is R intersect S the same as S intersect R? It is. Yes, it is. What about difference? Difference is not. Just like subtraction is not commutative, set difference is not commutative either. For similar reasons. The order does matter. All right. What questions do you have about these operations? We've got one or two more, but they're big ones. Yeah.
Why does union have to require that it's a column type? So can't you just tack them onto each other?
Tack them onto each other. So when I'm doing a union, like I said, it's a vertical. I'm sticking them on vertically, and so I can't just switch the data type of a column halfway through my result set, right? My result set is going to have one set of data types that has to match all of the tuples that it contains. So if I have a column that contains ints and a column that contains strings, I can't union that together because the data type. I'm sorry?
Is there a term for doing it vertically?
For doing it
horizontally?
Yes, that's what we're going to be talking about next. As a matter of fact, that's next up on the list. But before I do that, any questions? Any more questions? So for sticking sets together horizontally, this is probably another thing that you are familiar with through your math classes, through your set theory classes. Cartesian product. It's going to combine tuples from two relations combinatorially, meaning every single possible combination of tuples is going to be in my result set. And let me draw a little illustration, right? Just to refresh your memory on Cartesian products and what it means in this sense. All right, that's better. If this is column A and this is column B in this table, and then I've got column C and column D in this table, and I've got two rows in each. In my results set, I'm going to have eight rows, 8 tuples. And each of those tuples is going to have 4 columns in it. That's what a Cartesian product is going to do for us. So it's going to have columns A, B, C, and D. And the first row would be 1, 2, 5, 6. So the first row from this table combined with the first row from this table. The second one would be 1, 2, 7, 8, right? So every single possible combination of tuples that I can get. So then 3, 4, 5, 6, right? 3, 4, 7, 8. Actually, I'm sorry, I said that wrong. There would be 4. I said 8. There would only be 4. Sorry, my bad. There would only be 4 combinations, the ones that are up there on the board. Every single possible combination of tuples from these two tables would show up in the result set. So if we want to talk about this generally, right? You see the questions up here on the slide. You want to talk about this generally. If relation R has n attributes and relation S has m attributes, how many attributes are going to be in the result? N plus m. It's going to be the sum total of those attributes. The number of tuples in the result. So if R has n tuples and S has m tuples, how many tuples do I expect to see in the result? N times m, right? In this case, I had 2 tuples here, 2 tuples here, so 2 times 2 got me 4 tuples in my result, right? Every single possible combination of tuples. How is this useful to us? Cartesian product, getting every single combination of tuples like this. How is that useful to us? What real-world operation, what real-world thing does that mimic for us? How does that help us answer any questions? Yeah.
Kind of like a join, but it's way too many rows.
Well, you're getting to, yeah, you're one step ahead of me. The answer is that, no, it's good. It's good. The answer is that by itself, Cartesian product really doesn't help us too much. It's too broad. It's a very heavy-handed approach to combining these relations together. We want to have more control over this. I want to have more control over what relations are combined, how these two relations are combined together. I want to be able to specify that this table should be combined with this table, but is there some shared meaning between these two tables, right, that I can use to help me decide how to combine? And that's what leads us to the much more common operation. Yeah, I already talked about this. Much more common operation, which is a join operation. A join operation is defined as a Cartesian product combined with a select. Now, I mean the relational algebra select, right? Not the SQL select. So relational algebra select being a conditional, like a where clause, right? Some kind of a conditional. So here's an example of what a join looks like in SQL syntax. Select everything from employees, join salaries on, and then I specify an equality. This equality is saying that this column from the employees table means the same thing as this column from the salaries table, right? It's saying that those two columns mean the same thing. They represent the same kind of information. And so instead of just doing a brute force combination of all of the tuples together, I have a more meaningful combination of those tuples being combined together. What do those columns look like to you when I see columns equated like that? What am I going to use to help me pick these two columns? How do I know which columns are useful for me in that regard? Primary key and foreign key. That's why primary keys and foreign key relationships are so useful to us. One of these is going to be the primary key, probably this one in this particular example. The other one's going to be a foreign key in the other table. Those mean the same thing. And so this example is not a good one, but if I sketch out a more realistic one, real quick. More realistic looking example, if A is my if A is my primary key column, right? And over here, C is my primary key column, but D is a foreign key. Right? Actually, let me make this like a 4. No, that's not good. Let's make that I had it before. Now you can hopefully see what these results might look like. I'm going to try and do a Cartesian product, but every time I try to combine tuples, I have to provide an additional step. So I'm going to try to combine these two together, but I can only do so if A equals D in this case, since A is my primary key and D is my foreign key. Mark that. And so I'm looking for matches. Where does the 1 show up? Oh, there's no 1 here, so I'm not going to combine those two together. Right? That doesn't match my condition. But here's a 1. So I found a match, and so I'll include that. 1, A, 2, 1. There's a tuple in my result. Here's another. So I check the last one, and I don't see a 1 there, so I'm done with that row. And then I try to do 2. There's a 2, so 2B, 1, 2. I check this row next. There's not a 2 there, so I don't perform that combination. There's a 2 here, though, so 2B, 3, 2. And then the last row, I try to combine this row as well. I'm looking for 3s now, and I don't see any, so this row doesn't get included at all. It doesn't have a match. There's no match here. It's not included. It doesn't get included at all. So now instead of having, I would have had 9 rows, right? 3 tuples times 3 tuples would have given me 9 if I did a straight Cartesian product. But I didn't do a straight Cartesian product. I did a join operation. which just gave me these 3 rows instead of my result. These 3 tuples. Are there any questions about how that works, about how a join works? So a join is a Cartesian product with a select operation attached to it. Yes? Great question. So in this case, A is our primary key and G is our foreign key, which means that those represent the same thing in terms of information, right? And in the result set, as you just pointed out, it's a duplicate. This column is really a duplicate. And so there's a couple ways you can approach this. What I have done up here on the board, since I kept both A and D in my result set, that's what's called an equijoin. So an equijoin is the very strictest definition. Using the very strictest definition of a join, I'm gonna keep all columns in my result. But in practice, that's often not necessary to keep all of these columns, right? So there's 2 ways you could go about it. One is that you could perform a projection after this, right? To just get rid of one. But in practice, it's so common that there's another type of join that is a Cartesian product combined with a select, combined with a projection. That's called a natural join. So a natural join would do what you're suggesting, which is to chop off one of these 2 columns. It doesn't really matter which one we pick. Not necessarily. The only difference in this case is the name of the column. So that could make a difference, right? That could make a difference. In a lot of cases, these column names are going to be the same, so it makes no difference at all which one I get rid of. And so you probably already noticed that I'm sort of drawing this distinction multiple times between the theory that we're talking about and how that gets implemented. In theory, equijoin is probably what's used, and we'll project off afterwards. But in practice, that natural join is what you would expect to see on basically every single SQL database implementation. Great question. Any other questions? This is sort of known as like the big hurdle to learning SQL for a lot of people. Joins can be very confusing when you first start out. Best thing to do is get practice with them, especially if you think about this bottom piece of information. I can join more than 2 tables at one time if I need to, and you oftentimes will need to. You can see, though, that the syntax is kind of verbose. It requires a lot of information from me to do this. And so if I'm joining a lot of tables together, my queries can get very big very quickly. And those of you who have read and written a lot of SQL probably already have some of those monster queries burned into your brain that join a bajillion tables together, right? It happens. It happens. In this class, we'll try and keep it reasonable. Probably won't see anything with more than 3 or 4, which is still kind of a lot. But it's definitely doable. All right. Just to make things worse, there's another kind of join that we should discuss as well. So the kind of join that I talked about is called an inner join. It's called an inner join. I only include the tuple in my result set if the condition is matched, if the select operation is satisfied. An outer join actually says, well, you have to give me that condition, right? But I'm going to include tuples in the result even if that condition is not met. Even if that condition is not satisfied. And so how would that apply to us in this situation, for example? If I was doing an outer join, I would, there's actually 3 types here. So for the purposes of this example, the type that makes the most sense would be if I was doing a left outer join. Remember from before that this tuple did not have a match over here, right? Did not match. So a left outer join would say, all right, if I have a value from the table on the left literally means the table on the left side, I'm going to include it anyway. So I would have another row down here. Oh yeah, this board is busted. I forgot about that. I would have another row that says 3C. But then I have a problem, right? What do I include for the C and D columns for this tuple? Because there was no match. Right? I don't have anything to match it with. So what do I put in these columns? No, nothing. Yeah. So, in other words, an outer join is used to keep all of the tuples from one side of the join or both sides of the join. In the case of a full outer join, I'm going to keep tuples from both sides of the join. And if I have tuples that do not match, I'll still include them, but I'll just fill any missing values with nulls. Makes it very easy for us to then look at the results and see which ones don't have matches. Just looking for those null values. What could this be used for? Can you think of a use case as to why this might be something we'd want to do? So, yeah, go ahead.
Just say in a relation that we have possibly a one-to-one relation, but also there may be items in the left table that don't have matches in the right table.
Mm-hmm.
So, for example, departments that were just created that don't have any employees.
Exactly. So we're looking for things that aren't used, right? That's a common use case. I've got a whole list of stuff that is used, and I know it's used because I can run the query and see all the different times that it matches the criteria. But what if I want to know the stuff that's not being used? I can turn that into an outer join and look for those nulls, and then I know that for whatever reason, right, this is not being used. What if this join represented, employees in the departments that they're part of? I now know that this employee has not been assigned to a department. I can't answer that question with just a normal join, because that only shows me, with an inner join, because that only shows me what departments employees are in, if they have one. If they have one. It requires an outer join to answer the question of, show me the employees that don't have a department. And so the SQL syntax actually is very simple. Oops. The SQL syntax is very simple. I can turn this statement into an outer join by just including left, right, or full in front of the join. In front of the word join. That's all I would need to do. Now, in practice, only 2 of those 3 are used. The convention is to never write a right outer join. It's not necessary to do that. What would I do instead? Just flip the order and write a left join. So convention says you're either going to write a left join if I need to include one table, or I'm going to write a full join if I need to include both. I'm never going to write a right join. It's not. It actually will let you do that. The syntax is there, the code's there, but convention says don't do it. Any questions? Yes?
So if you're having a relationship where
Can you repeat that? I'm sorry, I just didn't quite hear you.
like if you have a relation with a foreign key, the foreign key is always going to have a
Yes, that's right. So referential integrity says, good. We talked about this last week. Referential integrity says I can't have a value show up in this column if it doesn't also show up here, right? That's the primary key, foreign key relationship. That's how referential integrity is enforced. So if I had done a right outer join here instead of a left outer join, I wouldn't have expected any difference. I wouldn't have expected anything different to happen because it's not possible for a value to be here that is not already here. So I wouldn't have noticed any difference in my results. But it is possible for a value to be in the primary key column and not in the foreign key column, right? So writing a left outer join, we may actually see these nulls show up as a result. Good observation. Any other questions or comments? Yes?
You said you'd only ever have 2 tables with a left outer join because you can have 3.
But you can still chain them together, and that's maybe not to make things too complicated, right? But I can combine So not only can I join more than two tables together, but I can have those be different kinds of joins. I could do a left join and an inner join, or a left join and another left join and a full join, right? And combine those two tables together. So it can get very complicated. It's not going to restrict what kinds of joins I can perform and what orders. Here's a question for you for an inner join, for the join that's on the screen, right? The join that's up here. If I swap the order of the tables, does that make a difference in the outcome? If I just take the two tables, I swap them, does that make a difference? Nope. Absolutely not. Same every time. And the reason for that is because I'm using the equality as my join condition. I'm using equality there. But for an outer join, it does matter. The order that the tables appear absolutely does matter. All right. So combinations, we've actually seen all of, well, there's one more actually relational algebra operation I'm going to show you in just a second, but we've seen all but one of the relational algebra operations that I'm going to show you in this class. Of the ones that we've seen, 6 of them are considered to be what's called a complete set. So select, project, union, difference, rename, and Cartesian product is considered to be a complete set of relational operations, meaning that any other relational operation that I wish to express can be done using those 6 operations in some combination. We've already seen examples of that, like talking about how a join is really just a Cartesian product and a select combined together, right? We've already seen things combining multiple operations together. And so one thing that you might notice is the intersection is not included on my in my complete set. So a little exercise that we might actually do if we have time is, how can I express intersection just using the operations? This is a pretty classic question that you might have already seen. I would like to keep moving for now, though, and ask you another very important question. So I do want to talk about this one. Of the SQL clauses that we have seen, right, what is the order that they are executed in? So if we go back to the first slide today that showed the clauses that we have been talking about in this class, right? Select, from, where, order by, and group by. Now that we've talked about relational operations and how they correspond to our SQL queries, let's talk about order of operations for a second. Which of these clauses happens first? From. Why? I agree with you, but why?
It's like selecting the table that is there.
So none of the other ones actually make any sense if I don't know what table I'm working with, right? Telling you what columns I want to keep makes no sense to me if I don't know what table I'm talking about. I don't know what table you're talking about. Or if we're using joins, right, what combination of tables I'm talking about. So from happens first. And notice that from is not the first thing that we write down, right? It's the second thing that we write down. But it's the first thing that we actually need to pay attention to. What's the next thing that we're going to look at? Where? Why?
We don't necessarily care about what we're returning on the table, just where to look for it at.
Where to look for it at. Here's a question for you. I actually agree with you that where is probably the next one on the list. Does it have to be the next one on the list? Could I do it later if I wanted to? I could, right? I could do where later if I really wanted to, but it makes sense for me to do it as soon as I possibly can. Why?
Selecting every single row from the table.
The more data I can get rid of, right, the faster it's going to go for me to do the other stuff. So where is going to eliminate things that don't match my condition, right? The faster I can eliminate data, the faster I can filter out the stuff that I don't want, the easier it's going to be for me to do the rest of my operations because there's just going to be less information around. So yeah, where is going to happen very, very quickly, as soon as we can. But it's also like, I'm going to put a little question mark here because in some situations, right, we may not be able to do it right away. We might have to delay it a little bit. We might have to do some other stuff first. So I do want to try to do it as fast as possible. In some cases, I can do it very quickly. In other cases, I might have to do some other stuff first. All right, what comes next? I'm sorry? Select. I could ask you the same question that I asked you about where, right? Do I have to do select right away? I don't have to, but the sooner I can chop off the columns that I don't care about, the easier it's going to be for me to do the rest of the stuff that I'm trying to do. All right, what's next? We only got 2 left, order by and group by. What's next? Yeah. So I guess the point I'm trying to make here when I say stuff like when it happens, maybe I should have been a little bit more clear. When I get to where and select, the order that those two happens is like kind of at the same time sometimes, or it's not always as straightforward as saying I'm going to do this entire condition and then I'm going to do all the select. It might be a little bit of both, interleaved with each other, right?
Like both or I guess select would have.
Select would have to happen by the time the group by happens, for sure. Yeah. So group by is the next on our list, which means that order by is last, which makes sense when you think about what order by is doing. Why would I want to sort things before I know what values are in the set to be sorted, right? Why would I want to sort stuff before I know what values are in the set to be sorted? Everything else is narrowing down what is in my desired relation, my desired result set, and order by then just sorts that result in whatever way I need to. So order by is going to be last. But the main takeaway that I want to, that I hope you got out of this is that unlike most programming languages that you're used to, this statement is not executed one after the other. And it might change from one statement to the next, the order that things happen in. I think from is almost always going to be first, right? But especially in the middle here with wheres and selects. And there are other clauses too that we haven't really talked about. We might talk about a little bit later on. But there are other clauses that I could include in this as well, where it's like, well, the order might be where and select this time. It might be select and where the next time for a different query. It kind of depends on a query by query basis what the order is that these things are happening in. And the reason why that's important is because we just talked about how each one of these clauses has a corresponding relational operation associated with it, right? And so if I give you a query, it is now our job as the designers of a database management system to decide how to execute that query. It's up to us then to decide, all right, I'm going to try to tackle the from clause first and then figure out how to do that. That's what I'm going to ask you to do on homework assignment number 2, right? And so we need to have some way of tracking what operations, what relational operations need to be performed and what order they're going to get performed in. What order do I want to perform these operations in? And so that all leads us up to kind of the main takeaway from this. I know I skipped a slide. I'm going to come back to that slide in just a second because it's very important. But all of that leads up to the main takeaway from today, which is now that we know these relational operations, I can take a query and I can construct what's called a query tree out of it. And a query tree is a data structure that's used to organize what operations need to be executed in order to execute a particular query. So if I give you a SQL query using the clauses that we've been talking about, right? How do I turn that into a series of relational operations? And what order do I execute those operations in? So real quick, we can actually make a very simple query tree and talk about some other things related to query trees as well. Let me erase some stuff here, give me some room. Okay. So I have an example query here, employee names and salaries. It's a pretty simple query, but you'll notice I didn't actually give you the SQL for it. So we can it's not a very complicated SQL query, right? But I know that all SQL queries are going to have a select clause and a from clause. So in this case, the from clause, the table that I'm pulling this from is probably the employees table, right? And And then the select clause is going to include name and salary, or is it? I actually think if we take a look, did I include the ER diagram on the next slide here? I did. It's a little more complicated than that because salaries is in a separate table. Whoops. So what does that mean we have to do? I'm taking data from two different tables. I got to join. I got to do a join. Got to do a join. All right, we got to do a join. So this will give us a chance to practice our join syntax as well. Join salaries on, and then I have to figure out what the condition is. And it should hopefully be easy. If the database was designed well, it should be easy. I should see a column name that appears in both tables that, right? If the database is designed well. Now, if it's not designed well, which there certainly are databases that aren't designed well, it might take a little bit more work for me to figure out what the relationship is between these two tables, how that's defined, what columns are involved. But in this case, employee number seems to be what we care about. In fact, I think we might have seen this query on a previous slide today, but just for completeness sake, employees dot TMP ID salaries. Yeah. And then I still have to fill out my select clause, which is the columns that I want, and that's given to us in the prompt, I believe. The names and the salaries. So looking at my ER diagram, I see I've got two name columns, first name and last name. It's a little ambiguous as to whether I want one or the other or both. To keep it simple, I'll probably just take last name and then salary. Last name, salary. So here is my SQL query for this particular problem, for the particular task at hand, and I want to take that query and turn it into a query tree, and we can use the order of operations that we just talked about to help us out with this, right? So we said from is going to happen first. So I look at my from clause, and I'm going to identify what tables are involved. Employees and salaries are the tables that are involved. I really wish I could move this forward, but I can't. All right. So then I'm going to build my tree from the bottom up, where the tables that I'm querying from, the from clause, are at the bottom. Employees, salaries. But I'm actually not done yet. I'm not done with my from clause yet, because I have a join. And I want to represent that join on my query tree. And I haven't told you what the symbol is for a join yet. It's actually just this figure here, which is called a bow tie. It's called a bow tie. For an outer join, it's actually also a bow tie, but in the case of a left outer join, you just like add little, I don't know, whiskers? I don't know what to call them. You have lines coming out of the left side, right, for a right outer join, and put lines over here for a full outer join. So join is a bow tie. In this case, it's not an outer join, it's just inner join, so you don't need the whiskers. You just need the bow tie operation. If I was doing a Cartesian product, right, I could actually just put an X for Cartesian product. But more commonly, we're going to see the bow tie for a join, and then along with that, I need to include the condition. So I'm running out of space over here, but employee ID equals employee ID. So I include the condition along with my join, and then I connect those to my nodes at the bottom. Everybody with me so far? Any questions on that so far? All of that was just to tackle the from clause. Since we had a join, it required a little bit more work. All of this was to tackle the from clause. So the next operation on our list is a where. I don't have a where here. I don't have a where. But if I did have a where, what would that look like on the tree? What's the symbol? It's the first one we looked at. Sigma. Where is a sigma? So I would include a sigma operation on my tree, right? I don't have one, so I'm not going to do that. I do have a select clause. What relational algebra operation is matched up with the select clause? What operation is that? Project, which is pi? Row. Thank you.
Pi.
Pi? Disagreement. Pi? All right. Pi?
It's pi.
Okay, thank you. And then I would include the columns that I want to keep, last name and salary, along with this last name, salary. And then I would connect that to the join node below. And in this case, we're done. I don't have a group by, I don't have an order by, I don't have any of that stuff to worry about, right? So in this case, we're done. This is a query tree. The tables will always be at the bottom. Any joins that need to be performed are usually going to happen after that to combine these two tables together. I'll list out the condition. Then I'll do any select relational operations or project relational operations after that, in the order that I want them to be executed in. So I think, again, it's important to understand that the execution here happens from the bottom up. If I'm interpreting that query tree, I'm going to start at the bottom and work my way up to help me decide what order those operations get performed in. Are there any questions about that process? Any questions about that? We will get lots of practice making query trees. On Wednesday, I'm going to ask you to do some, I'm going to bring in a whole boatload of practice problems, and we're just going to get practice applying these concepts that we talked about today. But I did want to back up for a second. I promised that I would back up to this slide. There was one clause that we didn't talk about, which is the group by clause. And recall that group by is actually related to an aggregate. So if I want to perform an aggregation, it's technically outside the realm of relational algebra, but it's such a common operation that it is important for us to be able to talk about aggregates in our query trees. And so the way that we do that is with this fancy letter F, which is short for function. So we really just consider the aggregate operation a function. And this can be used in a general sense as well. There are other functions that you may run into from time to time as you're writing SQL queries, and you could represent those functions in your query trees with this fancy letter F. And so you see an example here. The top one that you see is not an aggregate. I'm sorry, not a group by. I apologize. It is an aggregate. I want to see the average salary from the salaries table, but there's no group by involved. The bottom one shows a group by where the column that I'm grouping by is included to the left of my aggregate function. And so that's how we would include these on our query trees if we needed to do so. And we will see some examples of this probably on Wednesday. And so that should cover, I guess we didn't talk about order by, how to include that on our trees. I think maybe order by would probably fall under the functional category as well. There's not a Greek symbol for it that I'm aware of. All right. Any questions? Cool. So I want to wrap up today. How much time? I got 10 minutes? Cool. I want to wrap up today by talking about another concept very briefly. Again, a concept that you might have seen when talking about set theory in the past. This idea of relational calculus. So relational algebra is a procedural way of approaching a query execution. In other words, I do one operation followed by another operation followed by another operation. right? It gives us that order of operations that we're used to, where I read one thing at a time and progress down line by line. That is what relational algebra does. Relational calculus is a different way of thinking about how to define the results that you want to see. Instead of defining it as a set of operations to be performed, I'm just going to define the boundaries, right? I'm just going to tell you what the boundaries are of the set that I want, and then you're going to go off and find everything that matches those boundaries, satisfies those conditions, and include it in the results. It's a different way of approaching the problem, but they should both get me to the same place, right? They should both get me to the same place. And so, there's two different ways you can think about this. I'm not going to go into very much detail on either one. I'm just going to give you a very brief taste of relational calculus. I care a lot more about relational algebra. But a brief taste of relational calculus. So if I look at this first statement, this tuple calculus statement says that I'm looking for the first names from all of the tuples. That's what the first part of this says, everything before the pipe. The first name of all the tuples that are in the employee relation and have a birth date of after January 1st, 1960. Right? Domain calculus is a little bit more involved, where I guess the main difference between tuple calculus and domain calculus is that I'm specifying the conditions based on a broad domain, saying that I'm looking for columns U and V, where columns R, S, T exist in this relation and have a column R value of greater than January 1st, 1960. These statements are actually more or less equivalent. The domain calculus looks a little bit more complicated, in fact is, because it introduces this funny backwards E symbol. Does anybody know what that represents? There exists, good. So some of you have seen these before in set theory classes. So it's the existential qualifier. We're saying there exists a value that matches this in the specified domain, and whereas upside down A is called the universal qualifier, meaning every tuple must conform to the condition. I'm not going to ask you to write relational calculus in this class. That's not something that I am going to grill you on. I do want you to be aware of it, though, for one very important reason. When I write a SQL query using select, squares, froms, things like that, that is a relational calculus statement. I'm not telling you how to get that data back. I'm telling you this is the bounds of the set that I want to see from the database, right? It's a relational calculus statement. But how does that get executed? So computers don't do so hot with sort of open-ended, nebulous definitions like this, right? Computers really want things to happen in a first do this, then do this, then do this, then in a procedural way, right? That's relational algebra. Relational algebra is a procedural way. It says exactly, do this first, then do the next thing, then do the next thing, then do the next thing. So when we're designing a database, a SQL database in particular, one of the things that we are doing is providing a bridge between the relational calculus statements that people are submitting to us, the SQL queries, and the relational algebra statements that are easy for a computer to implement and execute on the back end. So anytime you write a select statement, right? Select from, where, etc., that's getting turned into a series of relational algebra statements that are being executed by the database management system on the back end. And you don't even see it, right? It makes no difference to you. You get the data back. That's what you care about. Well, in this class, we definitely care about it. That's what we care about a lot, as a matter of fact. And that's what you're going to be doing on homework assignment 2. Believe it or not, by the time you're finished with homework assignment 2, you'll be able to execute very simple SQL queries on your database. You'll have written a database system that can execute very simple SQL queries. It'll take some work to get there, but you'll get there. So that's kind of the direction that we are headed in. Does anybody have any questions? I think I have a quick practice problem. We do have some time left. We can do a quick practice problem before we go. But if you have any questions, I'd love to hear those now. All right. Does it matter which one we want to do? Either one. I'll leave it up to you guys. There's 2 practice problems at the end of today's slides. This one uses a join, whereas this one does not. And whichever one we don't do now, or maybe both of them, we'll do on Wednesday anyway, because Wednesday I have a lot of time specified to doing practice problems, to actually, getting you used to writing query trees for a given query, or backwards, taking a query tree and turning it into the original query. But we have time now, so I would encourage you, let's just do this one since it's the simpler of the 2. If you want to take a few minutes, write the query, and think about the relational operations that you would use. We should have just enough time. I'll give you a few minutes and we can chat about it real quick before you leave here today.
Select matches up with which clause though? Be careful. Relational algebra select is not the same as C. Right. That's right. So what operations? Sorry. You have to be more specific when you say select names. So you're talking about SQL select, or are you talking about relational algebra select? SQL select is the select operation here corresponds to like where. Relational algebra select corresponds to we didn't have it.
Okay, I am aware that we're running out of time, so we'll just do this one real quick, and we might take a deeper look at this problem in class on Wednesday real quick. I want to see the names and birthdays of all employees, so if I refer back to this ER diagram that we've been using a lot, right? What SQL clauses do I expect to show up in a query that answers that question? Select and from. So that should then hopefully already tell you what relational algebra operations I would expect to see in the query tree, correct? So from actually does not have a relational algebra operation associated with it unless I have a join involved, is there a join involved for this one? Nope, because both, name and birth date are included in the same table. And so the only relational operation that I need is what? The projection to grab the column. Or wait, do I even need that? No, I do need that, projection to grab the columns, sorry. So that would be about as simple as a query tree gets. I'd have the table at the bottom, a projection above that, done. Very simple query tree. We'll actually sketch it out on Wednesday. That's all for now though, so have a good week. I'll see you in a couple days.